This steam trap has failed. It's your job to separate the casing halves and inspect for damage. But one of the nut and bolt combinations holding the casing together won't budge. What do? Well, you have two choices. Split the nut so you can drive the bolt out from the bottom, or cut off the head of the bolt and drive the bolt out the other way. Either way, the right tool for the job is a cold chisel. The cold chisel is the simplest metal cutting tool. It's a length of square or octagonal stock with a flat beveled cutting edge on one end and a striking surface on the other. Eye protection is required whenever chisels are used. Striking force is provided by a ball-peen hammer or sledgehammer. The cutting edge of the chisel is held flat against the work while the hammer strikes the other end squarely. Because the cutting edge of a cold chisel is tempered or hardened, it can cut most metals you'll work with. Flat cold chisels are the most widely used metalworking chisels, but they're not the only kind. Among the other types you may use are the diamond point chisel and the cape chisel. Instead of a broad, flat cutting edge, cape chisels have narrow cutting edges that make them a good choice for cutting narrow grooves. And the diamond point chisel is for cutting V-shaped grooves and narrow inside corners. By and large, though, you'll use flat cold chisels more than any of the others. So let's spend a few minutes looking at flat cold chisels, how to select the right one for the job, and how to use and care for them. Before you can choose the right chisel for any job, you have to know what different types of chisels can and can't do. Cold chisels come in a variety of sizes, as you can see. And the sizes are classified in two ways, by the width of the cutting edge and by the overall length of the tool. Both the cutting edge and the length are important in deciding which chisel to use. The width of the cutting edge should be just a bit larger than the width of the work. This ensures that as much of the cutting edge as possible is used and that the full force of the hammer is directed against the work. The right length depends on how far the chisel has to reach to get to the work. If the work is out in the open and easy to get to, a short chisel can be used. But if you have to cut something in a hard-to-reach place, you have to use a longer chisel. I mentioned before that only ball-peen hammers and sledges should be used on cold chisels. That's because their striking surfaces are slightly rounded. This allows you to hit the chisel at only one small point. Hitting a chisel with, say, a carpenter's hammer, which has a flat striking surface, increases your chances of mushrooming the head of the chisel. Keep in mind, too, that the size of the hammer you use should be matched to the chisel. The wider and longer the chisel, the larger the hammer you need to provide enough force. If the hammer you're using is too small for the chisel, you're not going to get enough striking force to cut the work. In addition, you run the risk of the light hammer bouncing back at you or even shattering. Using too large or heavy a hammer presents the opposite problem. You could end up pounding the head of the chisel out of shape or cutting a lot more than you bargained for. A good rule of thumb is that the face of the hammer should be about twice the diameter of the chisel. Okay, now we know how to select the proper size chisel and hammer for a job. But what if the cold chisel you want to use looks like this? Its edge dented and chewed up, and its head mushroomed. This edge isn't going to cut the way you want it to. And on the first swing of the hammer, the mushroomed metal at the end is liable to break off and fly in all directions. You can get this chisel back in shape by grinding or dressing it. When dressing a cold chisel on a grinding or emery wheel, Be certain you protect your eyes with safety goggles or a full-face shield. And if the grinder you're using has a tool rest, make sure it's adjusted properly. When grinding the striking surface of a chisel, the tool rest should be perpendicular to the wheel. This way you can easily reshape mushroomed and damaged edges. Also, keep the chisel cool by quenching it frequently in cold water. This prevents the metal from overheating and becoming weak and brittle. A properly ground striking surface looks like this, beveled evenly all the way around to resist mushrooming. The cutting edge of a chisel must be ground at an angle of about 60 degrees and straight across the tip. If a tool rest is used, it should be adjusted to an angle of 60 degrees from perpendicular. In this way, the tool rest acts as a guide for dressing the cutting edge accurately. Again, be certain not to overheat the metal. And to preserve the durability of the chisel, don't remove any more metal than necessary. A little while ago, we watched a mechanic cut the head off of a bolt. Here, he's faced with a slightly different problem: a casing nut frozen in place. Before he can split the nut, he has to choose the right chisel. The largest of the three is too wide. Using it would not only waste a lot of effort, but would also cause uneven wear of the cutting edge. The smallest chisel is a hair too narrow, and it's not heavy enough to withstand the striking force needed to cut the nut. The last chisel, although wider than the nut, is not too wide, and it's heavy enough to tolerate sizable striking force. With the proper chisel selected, he makes sure to protect his eyes. He then selects the proper size hammer and sets the chisel in position against one of the flats of the nut. The first few strikes are very important because they get the chisel started and give it a solid bite on the work. Whenever you split a nut, cut off a bolt head, or do any other work with a chisel, the secret is to take your time. Hurrying might seem the fastest way to get the job done, but it's also the surest way to get sloppy results, damaged work, and sore hands. And remember, all your effort is wasted if you damage the threads of a stud or bolt. As soon as the nut is cut all the way through, stop to prevent cutting into the threads. To remove the split nut, you'll probably have to use an adjustable wrench. This is because splitting a nut distorts its shape, increasing its diameter and making it difficult to remove with a box end or open end wrench. Slow and careful work will split the nut with little or no damage to the stud or bolt. If the nut is large, or if turning the split nut might damage the threaded fastener, you might want to split the nut at opposite flats so the two halves of the nut will simply fall away from the threads. Once you finish the job, be certain to take care of your tools. This means proper cleaning and storage. For cleaning, a little light oil on a rag is best. Coat the chisel with a thin film of oil to protect it against corrosion. Do the same for the metal surfaces of the hammer. Once cleaned, both chisels and hammers should be stored where they'll be away from moisture, protected from banging around, and easy to find the next time they're needed. You can see that using chisels isn't difficult, but, like any other skill, It takes some practice to make cuts exactly the way you want them. In the next segment, we'll look at another family of cutting tools, tools that can cut everything from sheet metal to reinforcing rod and thin plate steel. As any sheet metal worker will tell you, the first step to working successfully with sheet metal is to carefully measure and lay out the shape you want before you start cutting. And when it comes to cutting sheet metal, you want a tool that's simple to use, a tool that you can control to follow the lines you've laid out. Metal snips fit that description. Snips are basically metal cutting scissors, and because scissors are familiar to all of us, they're easy to learn to use. Snips are divided into two types, straight and curved. The snips being used here are straight snips. They have straight blades and are best suited for cutting along straight lines. But straight snips, like these aviation snips, can also be used to cut wide circles and gentle curves. Notice that the cut is made on the waist side of the line. That's because the blades of most snips have small teeth that result in a slightly jagged cut. Leaving yourself some room on the waist side allows you to file the jagged edge without crossing the layout line. Straight snips, then, are okay for straight lines and wide curves. But for cutting small circles and tight curves, you need curved snips. The curve of the blades gives you better control, since they're specifically designed to cut curves and bends. Generally, then, there are two types of snips, straight and curved. They're sometimes found together in sets, as in this set of aviation snips. These are called aviation snips because they were originally designed for sheet metal work related to aircraft maintenance and construction. Today, they're found throughout industry. Notice that their handles are color-coded. The colors tell you exactly what kind of cutting each is designed to do. Red-handled aviation snips have blades that curve to the left. Naturally, you'd use them for cuts that curve or turn to the left. Green-handled aviation snips curve to the right. And those with yellow handles are straight snips, used, as we mentioned before, for straight cuts and wide curves. Regardless of which type of snip you use, remember that none of them cuts a perfectly smooth line. So when a smooth edge is required, cut on the waist side of the layout line so you have room for filing later on. Remember, too, that snips are light cutting tools, limited to sheet metal 1/16 of an inch thick or less. For cutting heavy sheet metal and thin plate steel, you need a heavier cutting tool. This is a bench shear. It gets its name from the fact that it attaches directly to a workbench or table. The heavy-duty cutting blade makes the bench shear an ideal tool for cutting metal that would ruin snips. And the long handle affords enough leverage for most cutting jobs. Like many other cutting tools, bench shears require occasional lubrication and sharpening. For cutting round stock or thicker soft metal, you can use a bolt cutter. It's a long-handled shear with adjustable compound hinges that give the jaws tremendous leverage. Bolt cutters are good for cutting studs, bolts, or reinforcing rod. Just be sure that the work is held steady in a vise or clamp. Position the work as far back in the jaws as possible and then squeeze the handles together. Bolt cutters will do the job as long as they're properly adjusted and cared for. Before using them, be certain their cutting edges meet along their entire length when the handles are closed. If they don't, tighten or loosen the adjusting screw until they do. And to keep the adjusting device and hinge in working order, oil them occasionally. Now, there's a limit to the type and size of metals that even bolt cutters and bench shears can slice through. For example, neither of them can cut through hardened metal like spring steel or thick metal like this keystock. So how do you know when metal is too hard or too thick for the tool you're using? Well, if you have to exert all the force you can muster to make the cut, you're using the wrong tool. Overstraining snips and shears isn't only a waste of time, it's also damaging to the tool and possibly to you. Let me give you some common sense tips you can use to get the most out of snips and shears. First, always get the metal as far back in the blades as possible. This increases your leverage and reduces unnecessary stress on the hinge. Next, keep the blades sharp. Dress worn or damaged blades with a file, being careful to remove only as much metal as necessary, while still preserving the original angle of the cutting edges. Finally, protect your snips and shears by storing them properly, some place where they won't bang against other tools and end up with nicked or dented blades. If you care for them properly and use them within their limits, you'll find snips and shears to be a really useful group of tools. You have to cut a few inches off of a length of angle iron. You know the exact measurements of the piece you need, and you're careful to lay out the job before you start cutting. But what tool do you use to cut it? Snips are far too light to cut angle iron, and shears would have a tough time biting through that 90-degree angle. The right tool for the job is this one, a hacksaw. The hacksaw is another tool that's familiar to most of us. It consists of an adjustable metal frame, a handle, and a replaceable blade. So if you find that the blade you're using is too long, or the teeth are the wrong size for the metal you're cutting, you can change the blade. Here, the blade to be replaced is removed by loosening the wing nut near the handle. When enough tension has been relieved, the blade will slip off the pins that hold it to the frame. If a longer or shorter blade is required, the frame can be adjusted to accept it. In this case, the replacement blade is shorter than the original. All hacksaw blades have either an arrow or a patch of color, or both, at one end. These markings tell you which way the teeth point and which way the blade must be positioned in the frame. The colored end of the blade or the arrow must be positioned away from the handle. This ensures that the teeth point away from the handle and that your cutting stroke will be the forward stroke rather than the return stroke. With the frame properly adjusted and the teeth of the blade pointed forward, the blade is hooked to the pins and the wing nut tightened. Be certain to tighten the wing nut securely. If the blade is loose, it'll wobble when you begin to cut. This not only causes an uneven cut, but can also lead to the blade breaking. Using the right blade makes the cut go a lot faster. And notice the technique the mechanic uses. He carefully controls his speed and rhythm. 40 strokes per minute is about right. Any faster, and the blade can overheat and weaken. Any slower, and cutting becomes more difficult. He also holds the handle with his index finger pointed straight out along the frame. This helps him control the blade. Notice, too, that he exerts pressure on the forward stroke and eases up on the return stroke. This is because the teeth of the blade are angled forward and therefore cut only on the forward stroke. If he failed to ease up on the return stroke, he'd not only be wasting energy, he'd also be wearing down the teeth of the blade. Just as important as the other points we've mentioned is the angle of contact between the work and the blade. We'll use this cutaway view of the angle iron to see why blade angle is so important. If the blade runs almost parallel to the surface being cut, then the maximum number of teeth are in contact with the work at all times. Angling the blade brings only a small number of teeth against the work at any one time. The end result is that more strokes and, of course, more energy are required to make the same cut. Earlier, we watched the mechanic replace one blade with another one, and the new blade performed far better than the original. One reason the replacement blade worked better is the size of its teeth. Let me show you what I mean. Here are three 12-inch blades, a pretty common length, good for most cutting jobs. One has rather large, coarse teeth, 18 of them per inch. The second has smaller, finer teeth, 24 per inch. The third one has very small, fine teeth, 32 per inch. Now, what's the purpose of the different sizes and numbers of teeth? Well, each blade is designed for cutting different types and sizes of metals. Here are two common metals you might have to cut: stainless steel and brass. Stainless steel is a hard metal. To cut it, you want to get as much cutting edge as possible on the work. So you'd probably use a fine blade, one with 32 teeth per inch. Even though the teeth on this blade are small, there are a lot of them, and the more teeth per inch, the more cutting surface per inch. If I tried this blade on the brass, it would probably cut it all right, but the teeth are so small that it would take a long time to finish the job. In addition, the soft metal chips would quickly clog the teeth. Since the brass is relatively soft, I don't need as many teeth per inch. So I'd probably use a coarser blade, one with 14 teeth per inch. Its teeth are larger, they'll cut faster, and they're less likely to clog. Your text gives you further information on which blade to use for which job. Just remember that, generally speaking, the harder the metal, the more teeth per inch you need. The softer the metal, the fewer teeth per inch you need. The blade you choose is also determined by the thickness of the metal you're going to cut. Here the mechanic is trying to cut relatively soft sheet metal with a coarse blade. When you push a coarse blade across a thin edge, each tooth catches on it. When he tries the same cut with a fine blade, however, he has very little trouble. With the fine blade, the teeth are small enough and close enough together to ride smoothly across the work. Now we've seen the way blades are designed, and we know something about what each blade is used for. Earlier, we watched a mechanic cut a section of angle iron, so I guess we know quite a bit about using a hacksaw. Well, let's see. Here's a problem for you. A rectangle must be cut from this piece of sheet metal. You can see the two layout lines, one vertical and one horizontal. The vertical cut is easy to make. But how can the saw make the horizontal cut? Cutting in from the side, the blade could only reach about halfway before the frame hit the edge of the work. Do you need a different cutting tool to finish the job? No. With a small adjustment, most hacksaws can make the cut. Just remove the blade and turn the pins at either end of the frame downward. Now, when the blade is hooked back on the frame, It'll be perpendicular to the handle. The cutting edge will face out toward the side of the saw. Just be certain to tighten the blade securely to prevent it from wobbling or breaking. With the blade adjusted like this, the saw can make the cut without the frame limiting its reach. Learning to cut like this takes practice because it's more difficult to control the path of the blade. But like other skills involving cutting tools, it's one that's well worth learning. Of course, no matter how careful you are with your hacksaw, the cut edge of the work will be slightly ragged. In many cases, that's unacceptable. So in the next segment, we'll look at a group of cutting tools that help you finish your cuts and do precision shaping. In the last segment, we cut a length of angle iron to size. But the cut's a little rough. The edges need to be shaped and smoothed. The right cutting tool for doing this is a file. As common as files are, and as often as they're used in maintenance and construction, there are a lot of misconceptions about how they're classified and how they're used. Files are manufactured in an almost unlimited number of types and sizes. But regardless of whether a file is short or long, flat, round, or triangular, what's important is the size and shape of its teeth. These flat files are good examples of the two types of tooth patterns. This one is a single cut file. Its teeth are a series of parallel ridges. The other file is what's called a double cut file. It has two sets of ridges arranged in a crisscross pattern. The crisscrossing creates hundreds of individual diamond-shaped teeth. Single cut files are used primarily for finishing work, like removing burrs and loose bits of metal, and for light filing jobs like dressing tools. Double cut files are fast cutting tools, ideal for shaping and for reducing rough cut metal to proper size. Like hacksaw blades, both single cut and double cut files are also categorized by the size of their teeth. The double cut files you see here are examples of the three categories available to you. The one with the largest, coarsest teeth is called a bastard cut file. This is a second cut file. Its teeth are smaller and less coarse, so a second cut file doesn't cut as quickly as a bastard cut file. Finally, there's the smooth file. A smooth file is not actually smooth, but its teeth are so small and fine that smooth files are well suited for finishing and shaping hard metals. These three categories, bastard, second, and smooth, apply to all files. Selecting the proper one for a given job will come with practice and experience. There are two other things you should know about files. First, they come in a variety of lengths. The length of a file determines how far apart its teeth are spaced. The longer the file, the further apart the teeth will be. So we can say that, as a rule, long files are coarser than short ones. The second thing you should know is that none of the files on this table are fit for use the way they are. Why? Because none of them have handles. Never use a file that doesn't have a handle or one that has the wrong size handle. The handle should cover the pointed end or tang of the file. Otherwise, you run a good chance of having the tang puncture your hand when you start filing. So, before starting any filing job, turn the handle onto the tang as far as it will go. There are two basic filing techniques, cross-filing and draw filing. The technique being used here is cross-filing. The file is moved in a crosswise direction, that is, diagonally and forward at the same time. Files, like hacksaws, cut in only one direction, so cutting is always done by exerting downward pressure on the forward stroke. On the return stroke, it's important to either ease up on the file or remove it from the work. This will keep the teeth from becoming dull. Cross-filing like this produces a fairly even surface, but a smoother finish can be gotten using a second cross-filing technique. Simply alternate the direction of your cutting strokes. Guide the file across the work first in one direction and then in the other. This will eliminate most of the roughness resulting from ordinary cross-filing. Where a really smooth and even surface is required, like the face of this flange, the best technique is draw filing. In draw filing, the file is always moved sideways across the work. Smooth, even strokes and equal pressure on both ends of the file are especially important. Remember, files cut in only one direction. If you're holding the handle in your left hand, the cutting stroke will be toward you. If you hold the handle in your right hand, the cutting stroke will be away from you. When the file itself can't make the surface any smoother, wrap some very fine abrasive cloth around the file. Then continue draw filing until you have the finish you want. Of course, not all the filing you do will require a flat file. As I mentioned before, files come in literally dozens of shapes. There's at least one to suit almost any requirement. There are half-round files, square files, triangular files. The list is almost endless. One file that's particularly interesting is the thread file. Basically, a thread file is a square file that has cutting ridges on its faces. Each face is marked with a number that tells you the pitch of the thread it fits. Here, for example, I have a shaft whose threads have a pitch of 20. It has a flat spot on the thread. I find the face of the file marked 20 and use that edge to repair the threads. Regardless of what kind of file you use, there are a couple of good tips that should always be followed. The best time to start caring for a file is when it's brand new. The way you break in a file affects how well it'll cut and how long it'll last. Get every new file off to a safe start by giving it a handle that fits properly. And for its first job, use it to file a piece of brass or other soft metal. This is important because the teeth on new files are slightly uneven, and filing soft metal evens the teeth out. Using a brand new file on a hard metal could cause the longest teeth to break off. To cut properly, file teeth have to be clean, and the tool for cleaning them is a file card. A file card is a very stiff wire brush whose bristles are arranged in rows. To clean this double-cut file, the bristles are run between the file teeth, first in one direction, and then in the other. To keep a file from clogging, or pinning as it's called, rub chalk between the teeth. This works especially well when filing non-ferrous metals, like brass and lead. Here, the side of the file that's been broken in is being chalked for the next time it's used. After breaking in one side, repeat the procedure for the opposite side and try to use all of the teeth on each cutting stroke. If you have to store files with other tools, wrap them in paper or cloth. This not only protects the file, but also protects other tools from getting scratched by the file teeth. So far then, we've looked at tools like hacksaws and snips that do rough cutting, and files that are used for shaping and finishing work. But none of the tools we've seen can cut with the precision needed to form threads for pipes and threaded fasteners. We'll look at the tools designed for that purpose in the next segment. All threaded holes start out as smooth drilled holes of one of two types. A hole can penetrate all the way through the work, or it can extend only part of the way through. Holes that extend only part of the way through are called blind holes. Of the two types, blind holes are more difficult to thread. To cut internal threads in a blind hole, you have to follow several steps and use more than one tool. Tools that cut internal threads are called taps. Taps are lengths of round stock that are threaded at one end and squared off at the other. Flutes are cut lengthwise through the threaded portion, creating sharp cutting edges. Taps usually come in sets that include three types: a starting tap that has a strongly tapered or chamfered end, a plug tap that has a much shorter chamfer, and a bottom tap, which has practically no chamfer. For tapping a blind hole, all three taps must be used, beginning with the starting tap. Taps cut threads by being turned into the drilled hole. To turn them, you use an open-end wrench or a special tap wrench like this one. The chamfered end of the starting tap is inserted into the hole and the wrench is turned to get it started. To cut accurate threads, the tap must go straight into the hole. Since this hole was drilled at right angles to the surface of the work, the tap must also be kept at right angles to the work. Lubricating the tap with cutting oil will keep it from overheating. And backing off on the tap every once in a while will dislodge any chips of loose metal and will prevent damage to the cutting edge or the threads. All internal threads must be started with a starting tap, because the long chamfer of the starting tap can get an initial bite into the metal. But this same chamfer makes the starting tap the weakest of the three types. As a result, a starting tap shouldn't be used to cut any more than the first 4 or 5 threads. These threads then provide a starting point for the next tap. For doing most of the cutting, use a plug tap. It's chamfered enough to cut fairly easily, but not so much as to make it weak. After the starting tap has cut the first threads, it is backed out of the hole. Before the plug tap is used, the hole must be cleaned out. When ferrous metal is being cut, a magnet is a handy cleaning device. The magnet will clear the hole of metal shavings that could clog the threads and jam the plug tap. When the hole is cleaned out, remove the starting tap from the tap wrench and replace it with the plug tap. Then turn the tap into the hole. Once again, technique is important. Be certain that the tap is thoroughly lubricated and alternate between cutting and backing off. Although the plug tap can do most of the thread cutting, its chamfer prevents it from cutting threads all the way down to the bottom of a blind hole. So once the plug tap is gone as far as it can, a bottom tap must be used. A bottom tap lacks the chamfer of the starting tap and the plug tap. This makes a bottom tap harder to cut with, but it enables you to thread a blind hole right to the bottom. Use the bottom tap just as you did the other two, and when it reaches the bottom of the hole, stop. Don't force it any farther than it wants to go. Back the tap out of the hole and set it aside. The final steps are to clean the last shavings of metal out of the hole and to check the new threads with a fastener or other part that has matching threads. If you've done the job correctly, the threaded part will fit as precisely as this one does. Seeing how a blind hole is threaded gives us a good overview of how taps work, because it involves all three types of taps. Threading holes that go all the way through are easier because you use only two taps, the starting tap and the plug tap. The bottom tap isn't needed. One thing we've ignored so far is how to select the correct tap or taps for a particular threading job. After all, there are several common shapes and sizes of threads in use today. Once you know what type and size threads are required, selecting the right tap is simply a matter of knowing how to read the code stamped on each tap. This tap is stamped NC 5/8 11. It means that this tap cuts national coarse threads, that its diameter is 5/8 of an inch, and that it has a pitch of 11. That is, it cuts 11 threads per inch. This tap cuts national fine threads, which are smaller and closer together than national coarse threads. Its diameter is 5/8 of an inch, and its pitch is 18. This is a pipe tap, used to cut internal threads in a pipe. It's stamped NPT, meaning National Pipe Thread, and this particular tap has a diameter of 1/2 inch. Your text has more detailed information about threads and taps, how they're classified and measured, and how to select the right one for the job. Regardless of what type of tap you use, though, remember that taps are cutting tools, and like any other cutting tools, they're useful only if their cutting edges are sharp. So, before using any tap, check its edges to make sure that they're sharp and intact. Using a dull or broken tap not only makes cutting very difficult, but can also lead to the tap breaking off in the hole. And to keep your taps sharp when they're not in use, store them in the manufacturer's packaging or wrap them in paper to protect their edges. In no way should you allow taps to bang against each other or against any hard surface in storage. Okay, we know about internal threads, but what about cutting external threads? For cutting external threads, you need a die and a die stock. This collet die consists of a die assembly with internal cutting edges and a holder called a die stock. Before starting the job, the die assembly is placed in the die stock. A locking screw on the side of the stock is tightened to hold the assembly firmly in place. The die is then turned straight onto the end of the work. Here again, the proper angle is extremely important if the threads are to be accurate. As with taps, lubrication of the die and work is crucial for minimizing friction and the damage it can cause. It's also important that the work be held securely in a vise to prevent it shifting around during the cutting procedure. As far as technique goes, cutting external threads is similar to cutting internal threads. The die should be backed off frequently to break off metal shavings and to permit additional lubrication. Earlier we saw that for cutting different sizes and types of internal threads, you have to use different sizes and types of taps. This same is true for dies. Right now, this collet die is set up to cut National Coarse 3/4 10 threads. If I needed to cut National Fine 9/16 18 threads, I'd simply change the interchangeable cutting edges. This is simple to do. I just unscrew the guide that holds the blades in place and remove the blades from their holder, called a cap. Then I set the National Fine cutting edges in the cap. And secure them by screwing the guide back in place. Now, collet dies are not the only dies you'll be using. This is another type of adjustable die, called a split button die. It's called a button die because of the arrangement of the holes in its center. The size of the die is adjusted by opening or closing the split. But not all dies are adjustable. Solid dies, like this one, cut threads on one and only one size of round stock. So you need a different size die for each different threading job. For threading pipe, you'd use yet another type of die, a pipe die. Pipe dies are larger and heavier than other dies and are not usually adjustable. This makes selection of the right die an important consideration. First, the pipe must be held securely in place. Threading the pipe is going to take a good deal of effort, so the pipe must be kept from moving. A chain pipe vise is ideal. To begin, the die is placed in a special die stock. Then the die is turned onto the pipe to be threaded. Notice that this pipe die stock has a built-in ratchet device. The ratchet saves the mechanic from having to swing the handle all the way around the pipe on each turn. It usually takes several turns before the pipe feeds far enough through the die stock to reach the cutting threads. When it does, it's important to stop and lubricate the die and the work. After that, the procedure is much the same as with any other type of die. One difference, though, involves backing the die off. Because of its ratchet device, the die can be backed off only by reversing the ratchet. This is done by adjusting the screw or lever on the side of the stock. Continue lubricating, turning the die, and occasionally backing it off until the desired number of threads have been cut. At that point, the die is backed off all the way. Then the new threads should be cleaned. In addition to wiping the threads, it's recommended that you coat them with pipe dope or oil to keep them in like-new condition until it's time to use them. In this segment, we've seen some of the basics of using taps and dies, but we haven't covered the whole field. Your text has more detailed information on the subject, including information on how to select the proper size tap or die for a job and which lubricants are best for various situations. Of course, all the cutting tools we've seen in this unit require special care. They do an important job for us, and to maintain their efficiency and precision, they have to be kept clean and in good shape. As you get more experience, you'll come to rely more and more on the tools you use, and if you're smart about your work, you'll treat all your tools with as much respect as you would other valuable equipment. And you'll realize that the extra time and care you put into using tools properly pays off in tools that are reliable for a long time.